All right, guys, here is the video going through lesson 2.5, and we're going to throw all of it into one video here, even though I know we spent multiple days on it. So we're going to hit all of the kind of last few formulas that we have on that unit circle sheet. So we'll have the double angle, half angle, power reducing, product to sum, sum to product. And so I know it sounds like a lot, so we'll try to break it down, say a little by little here. Most of these formulas are on that unit circle sheet. Say your double angle ones, your power reducing ones, sum to product, product to sum are all on there. They're kind of on the right hand side underneath the unit circle. The ones that are not on that unit circle that I would recommend adding somewhere, and so if you need to pause this video or go look at the notes on Schoology, say to find them. The half angle ones here are not. So get them on there somewhere, whether you want to put them on the back, put them kind of in the margins, wherever you can find room. But these half angle ones have like a plus minus sign because we're dealing with a square root here. And that plus or minus aspect all depends on the angle that you're dealing with and where kind of your angle lies, like which quadrant it's in. Depending on the context, you might have to look at like the original angle, like theta or x or u or whatever the variable it is you're working with. Sometimes you can just kind of work with the angle that you're given. And we'll kind of see that here when we get to the examples with those ones. But then tangent, you've got a couple options there. So either one of those two formulas, the 1 minus cosine over sine and sine over 1 plus cosine, those two should give you the same thing, say value-wise, either way in the very end. And then we have our product to sum, which is just taking like two angles that are being multiplied or two trig values that are being multiplied and turning it into something that's either added or subtracted. And we've got kind of all of our different combinations of like sine, then sine, cosine, then cosine, sine, then cosine, cosine, then sine. So though they're that order, that pattern with your trig functions is kind of going to determine which of these formulas you're going to want to use. The nice part is it is kind of formulaic, I guess, where u is just this first angle, v is the second angle, and we're just plugging those in for u and v in those four spots, and then we'll just simplify a little bit. So product to sum and then sum to product, same kind of thing. We'll have a u and a v that we'll plug in for u and v over in these things, and try to simplify where we can, okay? These ones we are kind of just going to stick to like these four, like sine, sine, either plus, minus, or cosine, cosine, plus, minus. So we're not going to look at a sine plus a cosine or a cosine plus a sine. Say those get a little bit funkier. So we'll kind of stick to more of the basic ones. But if we start with kind of our double angle and kind of like normal, I'm hoping it's okay that I kind of have everything written out to hopefully make this video go a little bit quicker. But if there's anything you need to pause, and then hopefully I kind of avoided any silly mistakes here. But we're going to find the values of sine 2x, cosine 2x, and tangent 2x given some certain information. So in this case, we're given a tangent value. So we're given tangent is 3/4, and that x is in between 0 and pi over 2. So that's essentially telling us which quadrant this angle is in, which is kind of help us determine sine and cosine values. And then over on the right, I just have our double angle formulas kind of rewritten there, so I don't have to like scroll back to the top just in case I want to reference them. So all I did to start with kind of was take that original information given here and use that to kind of get an angle somewhere here in quadrant 1, which then ultimately lets us kind of draw a triangle here and kind of use that tangent being 3/4 to kind of label two of our sides, 3 and 4, because this would be opposite, this would be adjacent, and then we could use our Pythagorean theorem, which I didn't actually show that calculation, but our Pythagorean theorem would give us 5 for that third side, which ultimately lets us find these two things. So it lets us find that sine x equals 3/5, cosine x equals 4/5. And again, drawing the triangle maybe helps you identify like positives, negatives, things like that. Because you could, in theory, use some of your trig identities to get those same values, but you'd have to be a little bit more careful as far as, okay, is sine a positive 3/5 or is it a negative 3/5? Is cosine a positive 4/5 or is it a negative? So I personally think just drawing the triangle helps make that piece a little bit easier. Plus the trig identities can get a little bit funky as well. But once we've got those two kind of trig values of sine x and cosine x, those are what all of these formulas are kind of revolving around. So needing those values. So if we're going to start with this first one here, like sine 2x, that's equal to 2 times sine x cosine x. Well, this thing and this thing are the two values that we just found, the 3/5 and the 4/5. So if I go over here and I say sine 2x is equal to 2 sine x cosine x, I'm just going to replace that sine x with the 3/5 that we said it was. I'm going to replace the whole cosine x with the 4/5 and then just simplify that as much as I can. And if it helps to look at this 2 as like 2 over 1, so then we just multiply straight across. 2 times 3 times 4 gets us 24. 1 times 5 gets us 25, so we end up with 24 over 25 for sine of 2x. Okay. If we then do cosine 2x, let me scroll up here real quick, because you've got like 3 options for cosine 2x. You got cosine squared minus sine squared, you got 2 cosine squared minus 1, and then 1 minus 2 cosine squared. That's not quite right. That should be 2 sine squared x, my bad. Doesn't matter which one you use. Personally, I like this one here just because if you end up with like a Pythagorean theorem number that's not a perfect square, say if you end up squaring a square root, then it ends up kind of canceling each other out. So I tend to go with that first one, but that's just me. So if I say cosine 2x is cosine squared minus sine squared, again, I'm just going to replace that cosine x with that 4/5. And if you haven't seen it before, cosine squared x is the same as cosine x squared. Say, writing it this first way just lets us not have to have the parentheses, so it saves us a little bit of writing there. So maybe cleans up notation within bigger formulas for maybe more complex math. Not really what I'm focusing on here. But what that means is we're going to take that cosine x value that we said earlier was that 4/5, and we're going to square it. Okay, so that's where that piece is coming from. And then I do the same thing with the minus sine squared. I'm just going to replace that sine x with 3/5, and then we'll square that. And now to square a fraction, all we have to do, square the top, square the bottom. So like 4 squared gets us to 16. 3 squared gets us to 9, 5 squared in both fractions gets us to 25. And the nice part with this formula, the cosine squared minus sine squared, 99+% of the time, if not every time, you're going to get a common denominator between these two fractions. So they're good to go, ready to combine. So then we could just do the 16 minus 9 and get the 7 over 25 or 7/25 for cosine 2x. Okay. Now in these problems, if you're having to find all like sine 2x, cosine 2x, tangent 2x, the formula for tangent 2x is 2 tangent x over 1 minus tangent squared, and that works perfectly fine. If you're looking for a different way to get that, that might be a little bit easier, an alternative formula for tangent of 2x is kind of taking that, like tangent being sine over cosine, identity that we used a lot in like 2.1 and 2.2. It's just now since we're dealing with tangent 2x, it's going to be sine of 2x over cosine of 2x. So if you wanted to add this like alternative formula for tangent 2x to your unit circle sheet, absolutely go for it. I personally like that one because the sine 2x and cosine 2x are the two numbers that we just found. That is the 24 over 25 and the 7 over 25 that we just found. So if I go down here and I want to find tangent of 2x using the sine 2x cosine, or divided by cosine 2x, well, I could just plug in the 24/25 for the sine part, 7/25 for the cosine 2x part. Then these 25s can basically cancel because they're the same denominator. And then I just end up with 24 over 7, which is maybe a little bit easier than doing the whole 2 times tangent over 1 minus tangent squared. If you wanted to use that other formula, it's not wrong. Say we should get the same value either way. Whatever way is easier for you or whichever way clicks more in your brain, go with it. Say stick with it and say do what works for you. Okay? So there's finding sine, cosine, and tangent of 2x. The other thing that we're going to do with this a little bit is just try to rewrite an expression as a double angle. And now not every trig function can be written as a double angle. Say these ones and the ones on like assignments, quizzes, tests, stuff like that will be kind of designed to work in that way. And so if we've got like 8 sine x cosine x, what I'm going to try to do here as far as like trying to rewrite it as a double angle is I want to kind of compare them to our double angle formulas and see which one is it kind of already closest to. And that 8 sine x cosine x looks kind of similar to this first one. It's just instead of having a 2, it has an 8. So what we could do is rewrite that 8 as 4 times 2, and then this 2 sine x cosine x, this is the same as sine 2x. So that whole 2 sine x cosine x is getting replaced by this sine 2x right there. And then I just have that 4 that we kind of factored out in a way, so I just end up with 4 sine of 2x. And now it's a double angle. Okay. Similarly, with this next one, I've got 6 cosine squared x minus 3. Well, again, if I kind of go over here, I've got a cosine squared minus sine squared. I've got a 2 cosine squared minus 1. I've got this incorrectly written one again. That should be 2 sine squared. Not that that one's going to matter because the closest one that we're looking like is this one here. Again, it's just I don't have a 2 and a 1. In this case, I've got a 6 and a 3. So if we factor out a 3 here, then we'd have 2 cosine squared x minus 1, which this whole thing basically gets turned into cosine 2x, which is where this part is coming from. And then I have that 3 that we factored out just kind of hanging around at the beginning. So it's 3 times cosine of 2x. Okay, so you're just trying to figure out like which one is it closest to, and maybe is there something I have to factor out to get like that specific formula to get it rewritten as a double angle. Okay. So the next kind of chunk here is what we call the power reducing formulas, which are a little bit kind of funky. It's a lot of algebra stuff. So if it's algebra pieces that kind of give you a little bit of trouble, this might be a little bit challenging for you, but we'll try to break it down. So we're going to use the power reducing formulas to rewrite the expression in terms of the first power of the cosines of multiple angles. So basically what that piece is saying is take something with a like sine to the third, fourth, fifth, or cosine to the fourth, fifth, something like that, and turn it into something that it might look kind of more complicated, it might look uglier, but it's just cosine without any exponents. So it's like cosine of 2x, or maybe it's 3 cosine of 2x or something like that, but at least we don't have exponents. We're trying to get rid of the exponents in this case. Now, if we're going to start with sine to the fourth, or sine of x to the fourth, we don't have a power reducing for something raised to the fourth. All of ours are based on squareds. So what we would have to do first in this case is start by breaking down sine to the fourth into sine squared times sine squared. Just like x to the fourth is x squared times x squared, or y to the fourth is y squared times y squared. Sine to the fourth is just sine squared times sine squared. But then we could use that sine squared x power reducing formula, turn each of those into 1 minus cosine of 2x over 2. Okay, and again, because we have 2 of them, we're going to get the same exact kind of fraction twice. And now I am going to want to take those kind of 2 blue fractions that we have here and multiply those together. Now the bottom part's easy. 2 times 2 just gets us 4. But this top part, the 1 minus cosine 2x times 1 minus cosine 2x, that's kind of a FOIL problem in disguise in a way. So I would have to do the 1 times 1 to get 1. 1 times negative cosine 2x is this negative cosine 2x. Then my inside gets me another negative cosine 2x, which is that part. And then negative cosine 2x times negative cosine 2x gets me positive cosine squared of 2x, which is that last piece. And then, like I said, that bottom part is just 4. Now, the two middle terms here, say we can combine, so that negative cosine 2x minus another cosine 2x is just negative 2 cosine 2x. So those two got combined into one term. So simplify a little bit. Now, with multiplying all that out, it does pose a little bit of a problem for kind of what we were trying to do here, because when we did the negative cosine 2x times the negative cosine 2x, it gave us that cosine squared, which again, we're trying to get rid of exponents within this thing. So what we're going to have to do is this piece here, this cosine squared 2x, we're going to have to do a power reducing formula again on this one. So that cosine squared 2x, we're going to need this part here. And now this piece gets a little bit funky because the power reducing formula is kind of based on just having an x here. So like this part kind of matches up with this, or whatever's here kind of goes here. But now in my actual problem, this cosine squared 2x has like a 2x here. So it's a little bit more than what our kind of formula looks like. So ultimately what's going to happen is this 2x, so that I have in my problem, is kind of what's going to get plugged in for x in my power reducing formula. So what that's ultimately going to give me is like the 2 that comes from my formula times the 2x angle that we have. So when I do that power reducing formula over here, okay, I've got my 1 minus 2 cosine 2x, we had that previously, but then that cosine squared 2x is going to turn into 1 plus cosine of 2 times 2x over 2, and then that's all over 4 yet. So then that 2 times 2x is ultimately going to turn into a 4x. So that we have there. But again, the whole goal here was to try to get rid of exponents, which is what we did. We were able to accomplish that, even though our like number being multiplied to our angle x is getting bigger, our exponents are now kind of gone, which is ultimately what we wanted. And now to try to simplify this, if we can, okay, so we did the 2 times 2x to get the 4x, and now I still want to try to get that like little fraction within the bigger fraction simplified. So if you wanted to kind of do what we've been doing with like getting common denominators between all of our different terms, like we could rewrite the 4 as 8 over 2. We could rewrite the 1 as 2 over 2. And then with this 2 cosine 2x, if we're going to get a common denominator, all we'd have to change is this front 2 into 4 over 2. But if we did that, then this 2, this 2, this 2, and that 2 are all going to cancel. And I'm going to end up with 2 minus 4, so that 4 cosine 2x, plus, say I'll have this denominator as it's, or not denominator, numerator, as it's written, so just the 1 plus cosine 4x, all over 8, because I'm canceling that 2, so that 4 is kind of turning 8 over 2, and I just have the 8 left over. And then our last little thing here, if this hasn't been enough already for one problem, say the 2 and the 1 here we could combine into a single term, and we would just get 3 minus 4 cosine 2x plus cosine 4x over 8. Okay. Which again, ultimately our goal was to try to get it written as cosines raised to the first power. Okay, try to get rid of any exponents that we can, and say that's what we were able to accomplish. Even though it looks a lot kind of messier than what we started with, say we were able to kind of get done what we wanted to. Okay. Going on to half angle formulas then. So half angles are going to be maybe a little bit more similar to the double angles that we kind of started with. Just different formulas that are maybe a little bit more complicated looking. And so if we're going to use the half angle formulas to find the values of sine x over 2, cosine x over 2, and tangent x over 2, kind of like our double angle formulas that we kind of started with, we're given some information as far as like a sine x equals 3/5, and then we have x between pi over 2 and pi. So that piece over here kind of tells us where our angle lies. So it's in quadrant 2. And then sine being opposite over hypotenuse means we could label that side as 3, say that side is 5. And then if we did the Pythagorean theorem, we would get like A or B, whichever one you kind of keep in there, as 4. The thing we got to be careful with though is since our side is going to the left, that is technically going to be a negative value. So that would be -4 for that adjacent side, which tells us cosine x equals -4/5, which that's a big piece of information because our sine x over 2 and our cosine x over 2 are both relying on a cosine x value, okay? And that's the piece that we just found was -4/5. So that's what we're going to be able to kind of plug in there. And then tangent relies on sine and cosine, so we were going to need that anyway, and we already have the sine function, or sine x. It was kind of given to us at the beginning. So we should have everything that we have to kind of find all of these answers, and then we'll kind of talk about, say now, like how do we know whether it's plus or minus, because it's not going to be both. It's going to be one or the two depending on the angle that you're dealing with. So if we start with sine x over 2, I'm going to just keep the plus or minus sign in there to kind of start with. But then I would have plus or minus square root of 1 minus, and then my cosine value is at -4/5, and that would all be over 2. And now with simplifying this minus and negative is going to turn into the plus here. So I've got 1 plus 4 over 5 over 2. Then within that kind of square root piece, again, I have like a little fraction within a bigger fraction that I want to try to simplify. So maybe I just get everything in terms of like a denominator of 5. So like that 1 is turning into the 5 over 5. Say that 4/5 can stay. 2 is turning into 10 over 5. And then these denominators of 5 can cancel. And so I've got 5 plus 4 is 9. Over 10, and now if you want to leave it like that, you can. If you wanted to get like the most officially mathematically correct answer, it would end up being 3 root 10 over 10, because if we were to take square root of 9 over 10 and look at it as root 9 over root 10, that would give us this, say 3 over root 10, which we would then rationalize to get 3 root 10 over 10, okay? So that's kind of the value within the square root number. But now as far as like the whole plus or minus piece, okay, if we are given our original angle is in quadrant 2, okay, somewhere in there. If we know our original angle is in quadrant 2, it's got to be somewhere between 90 and 180. Well, if I were to take that original angle and like our kind of piece here says, divide it by 2, okay, if this was originally x, if we take any angle in quadrant 2 and divide it in half, that x over 2, or that original angle divided by 2, is going to end up somewhere in quadrant 1, okay, because even if I go on the lowest end, 90 divided by 2 gets me 45, that would be in quadrant 1. If I go 180 divided by 2, that gets me 90, which I know technically maybe isn't in quadrant 1, but it's not in quadrant 2 either. It's right on the y-axis. And so even if you went just a tiny bit smaller than 180, if you went 179 divided by 2, that's going to get you an angle in quadrant 1. So in quadrant 1, sine is positive, and cosine is also positive. So with this whole plus or minus sign, since in quadrant 1 sine is a positive, I know my overall answer in this case is going to be a positive, which we don't normally write a positive sign, so that's why I didn't have it here. We just kind of assume it's the positive in this case, okay? And then even this little diagram here, say this kind of lets us know what this sign as far as like positive, negative is going to be on our cosine of x over 2. Okay, so when I go down here to cosine of x over 2, I'm going to get something really, really similar. Okay, and again, when I go from like this first step to the second one, this plus or minus sign just kind of almost goes away a little bit. Or again, because of this piece here, I know that my final answer should be positive. So after the first step, I just stopped writing it, okay, because I know it's going to be, say, the positive version, okay? But as far as like the simplifying piece, the only difference between sine x over 2 and cosine x over 2 is now I have a addition sign in the middle. So then I end up with 1 plus negative 4/5 over 2, which we don't have a double negative in this case, so I end up with 1 minus 4/5 over 2. Again, I can get a common denominator of 5 to be able to cancel all those things, and it's just instead of 5 plus 4 to get the 9 that we had in our sine answer, it becomes 5 minus 4 over 10, which is 1 over 10. Again, if you want to leave it like that, or if you wanted to take the square root of 1 as still 1 over root 10, rationalize and get root 10 over 10, either one of those answers is perfectly fine by me. Okay. Then tangent of x over 2 is a little bit different. We don't have any square roots. We don't have any plus minus signs to worry about. Say tangent, the only kind of thing you have to decide is which formula do you want to use, because you have 1 minus cosine x, or you've got sine x over 1 plus cosine x. You should get the same answer or the same value either way, so it shouldn't matter which one you pick. I like the 1 minus cosine x over sine x, maybe just because it comes first on the sheet. So that's the one I went with. And again, tangent kind of relies on both cosine x and sine x values. So our cosine we found earlier was the negative 4/5. So that's just getting plugged in there. And then the sine x was the one we were given. So that's our 3/5. So that's where this bottom part is coming from. Oops. Then if we kind of take care of the double negative here, so that's where we're getting the plus sign from, and then at the same time I just turn the 1 into 5 over 5 just to get my denominators all being 5, so I can kind of cancel those and get 5 plus 4 is 9 over 3 ends up just being a regular old 3. Okay. So like I said, tangent answers look usually a little bit nicer. We don't have any, say, square roots, no plus minus signs to worry about. It's just picking one of the two formulas, plugging in your sine value, plugging in your cosine value, and trying to simplify where you can. Okay. Similar type of problem, still dealing with half angle formulas. So we're going to try to find the exact values of sine, cosine, and tangent using half angle formulas. Now, rather than being given like, okay, sine is 3/5 and it's in quadrant 2, or tangent is 4/8 and it's in quadrant 1, something like that, we're just given an angle. So we're just given 165 degrees. And now if you're trying to use a half angle formula, what we want to try to do is get 165 rewritten as something over 2. So they try to get it written as x over 2 to be able to kind of use our half angle formulas. So because we want it as something divided by 2, to figure out what that something is, if we take that angle that we're given and multiply it by 2, this is going to give us that like something. It's going to give us that x. Okay, so that if I did 330 divided by 2, I get back to that 165. Okay, so that 330, like I kind of have over here, is what we're going to be plugging in for these x's. Okay, and it would go in for, say, these ones as well. And so when we do that, okay, I've got sine of 330 over 2, which is just another way of writing sine of 165. So I've got that 1 minus cosine of 330 over 2. Now cosine of 330 is something that we can find from the unit circle. So that root 3 over 2, say this piece here is coming from unit circle. Okay, so that's just going to be different based on the angle that you're working with. Okay, it might be root 3 over 2, it might be negative 1/2, might be negative root 2 over 2, who knows? Okay, but then again, we're going to want to try to simplify as much as we can. And now these ones we're not going to be able to get as far as we were in the previous couple of examples, just because we kind of now have a square root inside of a square root, which is not really going to be able to get simplified too much. But I think it would still be a good idea to try to get rid of the fraction and a fraction. So if we take that 1 and turn it into this 2 over 2, because then we can cancel all of these 2's, and I kind of also did the same thing with the bottom part, so I turned the 2 into 4 over 2, like I said, to kind of be able to cancel all these things. So then on that top part, I end up with 2 minus root 3. Well, 2 minus root 3 can't really be simplified. So that's just going to stay 2 minus root 3 over that 4, all within another square root. Now, what we could do, and what I would kind of like to see us do here, is we could take the square root of this top part divided by the square root of the bottom part. And I like that because then the square root of 4 can just turn into a regular old 2. So then at least we don't have a square root over everything. It's just like a square root on the top part. So it simplifies it a little bit there. Again, still doesn't look super pretty, but it's at least a little bit more simplified. And then our cosine answer is going to kind of come from, again, very similar formula. It's just now I have 1 plus cosine of 330. So that cosine of 330 is still root 3 over 2. It's just now I have 1 plus root 3 over 2 over 2. And so if we, again, try to simplify, what you might notice is if you kind of compare your final answers, because again, all that's changing between sine and cosine here is this thing in the middle. My 1 is still turning into the 2 over 2. The 2 is still turning into the 4 over 2. So all of that is kind of working the same way. I'm still canceling like all of these little denominators. And so I end up with almost the exact same answer. Say our original or our sine x over 2 is 2 minus root 3 over 4. Here we just have 2 plus root 3 over 4. So it's almost the same thing, just a different sign in the middle here, which again, if we square root top bottom, that square root of 4 can turn into 2. The other thing that we kind of needed to worry about here, and maybe I should have mentioned something on the sine answer, that whole plus or minus sign, we do still need to worry about that. Now, the nice part with just having just a number given to you, you know exactly where that angle is. 165 is in quadrant 2. And in quadrant 2, so yeah, 165 is in quadrant 2. Say quadrant 2 means sine is positive, cosine is negative. So that's why that sine of x over 2 or sine of 330 over 2 was just the positive square root. And then cosine of x over 2, so we've got this negative sign that's kind of carrying through here. And our final answer ends up being a negative. Say that the location of that 165 in terms of like which quadrant it's in, that's what's kind of dictating that. Okay. If it had been like if it had been 330, okay, 330 is in quadrant 4 where sine is negative and cosine is positive, then that would have maybe switched up some things, say for my final answers there. Okay, or if it had been 280 or something like that, okay, something in quadrant 3, then both of them would have been negative. Okay. But then, say if I jump down to kind of the last one dealing with this kind of setup, I've got tangent of 330 over 2, which again, say tangent, don't have to worry about the square roots and the plus minus and stuff like that. It's just now I need both cosine and sine. So I'd have to go back to my unit circle to figure out, okay, what is sine of 330? Well, sine of 330 is negative 1/2. And so, I'm using the 1 minus cosine x over sine x just because that's the one I kind of randomly chose. And so, again, that cosine is getting replaced with the root 3 over 2, and then the sine gets replaced with the negative 1/2. to get that original kind of set up. And then if we take the 1 and write it as 2 over 2, then we could cancel all of those 2's, and I get 2 minus root 3 over negative 1, which if we wanted to simplify that a little bit more, we could split that into like 2 separate fractions of 2 over negative 1 minus root 3 over negative 1, which would get you negative 2 minus negative root 3. And then that double negative there would turn into adding, which gets us negative 2 plus root 3 for a final answer there. Okay. So those half angles are tough. So they're kind of tricky. They're a little bit finicky there. So especially with those ones, if you need help, say let me know. So I'm happy to help you out with trying to figure out what the plus minus sign is, or the simplifying. So I know those are a little bit tougher. But hopefully, to kind of finish out a little bit easier, we've got our product to sum and sum to product. And again, which formula you're using all kind of depends on the order of, is it sine then cosine, cosine then sine, sine then sine, cosine then cosine. So that all kind of dictates that. So if we're going to use product to sum, we've got 2 trig functions that are being multiplied right now. So I got 10 sine of pi over 4, cosine of pi over 4. And so since it goes sine, cosine, I'm going to my unit circle sheet, and I'm going to try to find the sine u cosine v. And then in this case, basically we're going to say u is that first pi over 4, the v is the second pi over 4. So in this case, since they're both pi over 4, doesn't really matter which one's u and v. If they're different angles, then it certainly does. But we've got the sine u cosine v is equal to that 1/2 sine u plus v plus sine u minus v. So again, we're just going to basically plug in the pi over 4 for each of these angles. And so that's how we're kind of getting this part in blue. And then that 10 that we had at the very beginning of the problem, because it was 10 sine pi over cosine pi over 4, that 10 is just kind of going to hang out at the front. It'll get multiplied with that 1/2. And so that 10 times 1/2, that's where we're getting this 5 from. And then once you've got like your u and your v kind of plugged in, all we're going to try to do is simplify that down to like a single number. So like pi over 4 plus pi over 4 is 2 pi over 4, which would simplify down to pi over 2, which gets us this thing. And then pi over 4 minus pi over 4 is 0, which gets us sine 0. And then that's where we're going to leave it, okay? We could go further, we could actually figure out what sine of pi over 2 is, what sine of 0 is, figure out what those values are, and actually get this down to a single number. So that's not I guess, my purpose for having you kind of do these ones. I just want to see more, can we switch something that's starting as like 2 things being multiplied, and can we switch it into something where we have addition or subtraction happening? Because if we really just wanted to get it as like a single number, well, we could take the original and figure out what sine of pi over 4 and cosine of pi over 4 is, and we won't need any of this other stuff. So again, just get it down to a single kind of number for each of your angles, say here and here, and then you're good to go. Okay, and simplify anything that you have out front. But so hopefully that's a little bit easier than maybe the half angle, because then, so product to sum and then sum to product, very, very similar. So again, we're just kind of going the other way around, where I've got 2 things that are maybe being added or subtracted right away, and I want to turn it into maybe 2 things that are being multiplied. So if we're going to start with cosine of 120 plus cosine of 30, again, I'm going to kind of take a look at, okay, it goes cosine, then cosine. That's how I'm kind of determining which formula to use. And so I found the cosine u plus cosine v is equal to 2 cosine u cosine v, 2 cosine u plus v over 2 cosine u minus v over 2, sorry. And we're basically saying that the 120 is u, the 30 is v, and so I'm just going to plug in, say, the 120, the 30, the 120, the 30, and that's how we're kind of getting the blue part. So the 120 plus 30 over 2, 120 minus 30 over 2, and then just like the previous ones, we want to just try to simplify that down to a single number. So 120 plus 30 is 150, divided by 2 gets you the 75 here, and then the 120 minus 30 is 90, divided by 2 gets us the 45, and again, that's where, so we're going to leave it, okay, just as an expression with two things being multiplied versus being added, okay. So again, I know like a lot of these things are kind of varying levels of difficulty. Personally, I think like the half angle and the power reducing are a little bit tougher. I think the double angle and maybe the product to sum to product are a little bit easier. Everybody's a little bit different though, so maybe some things click better for you, and if that's the case, awesome.